He's employed full-time at Microsoft in Pittsburgh, and he runs a website called Chain Tuts. He provides articles and videos and code projects which break down core cryptocurrency concepts. Really happy and pleasure to introduce Josh McIntyre.
Well, thank you everyone so much for being here. I hope you enjoy it as much as I'm going to enjoy being up here teaching you. So today we're going to be breaking down proof of work. And what I want to do with this session is welcome in folks that don't necessarily have a computer science background to still understand, yeah, I see someone in the back's excited. I want to break down and help people understand how proof of work actually operates, sort of at an algorithmic level, but without you having to have a background where you know exactly what a cryptographic hash is, know about binary numbers or probabilities. So we're going to be doing a really cool simulation using these Adafruit microcontrollers, and they're spread throughout the room. I have ones with battery packs as well as cables, USB cables you can plug into your laptop, and even pull some data off there. So first, I always like to just give a little bit of background about myself and what I'm interested in and sort of what my biases are. So I'm a full-time software engineer at Microsoft in Pittsburgh, doing sort of full stack development unrelated to crypto. But my side project and my labor of love is this chain tutorials website at chaintuts.com, where I write articles, videos, and code projects and really try and break down cryptocurrency concepts so you can better understand how different components of systems like Bitcoin work. So you can find me on the website and on some social media, and I encourage you to check it out and share it with your friends. So in terms of what interests me the most in the crypto space, I'm interested in really how it works and why the way that these decentralized currencies function is so important for society. So I don't really pay attention much to like the investing side, and I try to just keep things educational and really focus on kind of what Andreas said in his keynote, which is continual learning. So why do we need proof of work in the first place? In traditional payment systems like credit cards, PayPal, other Venmo, those sorts of platforms, we have to trust a central authority to process payments and make sure that everything is sort of correct when doing a transaction. So if Bob pays Alice via PayPal, PayPal sits in the middle of these two and has to verify that Bob has the amount of money that he says he does, and make sure that the final settlement occurs on Alice's end. But a lot of us, as we're familiar with Bitcoin, we know there are no intermediaries. Bitcoin is a completely peer-to-peer and decentralized system of money. So this is fantastic, but it comes with some issues at a fundamental level, which is how do we prevent fraud? How do we prevent transaction issues like double spends and that sort of thing that the sort of chain of digital signatures blockchain ledger doesn't solve in and of itself? So on the Bitcoin blockchain, everyone running the Bitcoin software, at least if you're running a full node, gets a copy of this distributed blockchain ledger. And this behaves kind of like a sort of spreadsheet that shows all the transfers between parties. So when you send money to somebody else, this is a transaction that's recorded on the blockchain. And every 10 minutes, all of the pending transactions that haven't been processed yet are batched together into what are called blocks. And this batch processing contains a security challenge called proof of work. And this is how we're going to avoid problems like the double spend problem. So each Bitcoin block contains transaction data and metadata and what's called a proof of work nonce, which is essentially a random number. This gets run through a one-way function called a cryptographic hash function. So when you run some data through a hash function, it's only one way. You get a hash value, an output of that function on the other end of the hash, and you can't go backwards to the original data. So when you hash something, you get this value, and there is no way to go backwards to what the original data was without essentially guessing a bunch of times. So this is part of the proof of work algorithm. The block header data and the nonce get run through this one-way cryptographic hash, and this final hash that we get has to meet certain requirements as part of the security challenge. So the only way to find a nonce value that will meet the guidelines of the proof of work security challenge is to guess a bunch of times. And in Bitcoin, it means guessing really a lot of times. There's no formula or predictable outcome that can help you help a miner find the proof of work solution. It's all raw computing power and guessing. But once the answer to this problem is found, anybody can run the block data back through the cryptographic hash and verify that the answer is in fact correct. So Bitcoin nodes will share and verify the shared blockchain ledger and ensure that these rules and security challenge guidelines are followed. So nodes on the Bitcoin network are going to ignore any sort of malicious blocks that don't fit this security challenge rule. So again, we said that you have to guess a bunch of times. You have to expend a ton of computing power and energy to solve the proof of work problem. So when we talk about a gigantic network of people mining and doing this problem solving with all of their computing power, it turns out that any attacker that would try to pass off a block with fraudulent information in it, say, oh, I got 50 Bitcoin from Alice and not 1, they would have to outcompute the entire rest of the Bitcoin network within the 10-minute batch processing time to be able to pull off a fraud and have their block recognized as legitimate. And this is nearly impossible to do at the scale of these cryptocurrency networks. So at the time that I did these slides, Bitcoin had 75 quintillion proof of work guesses per second. And it takes on average about 10 minutes to find a solution to this problem. That's how astronomical the amount of computing power that goes into proof of work is. On the Bitcoin Cash blockchain, there's about 2 quintillion, and we're in the trillions, hundreds of trillions for Ethereum and Litecoin. And these are all considered to be pretty decentralized currencies. Even if you had a data warehouse full of mining ASICs to try and pull off some sort of fraudulent action on the network, it's impossible at the scale of these actual decentralized blockchains. So now let's dive in a little bit more with our simulation and talk about what the proof of work security challenge actually is. So remember I mentioned we have this one-way hash function that outputs some data. And this data in computers is really just bytes. And it turns out that these bytes are really just numbers. We can think of this block of data as an integer number represented in binary. So the challenge is we want to find a nonce random value by guessing so that when the block header data and the nonce are concatenated together and run through the hashing algorithm, the resulting number in that hash is going to be less than a special number called the difficulty target. So it turns out that the lower that this difficulty target number is, the harder and harder it is to find a solution. So it's a probability. On average, it takes longer to find a guess that gives you a hash output meeting these requirements, the lower that the difficulty target gets. So Bitcoin adjusts this difficulty target so that on average a proof of work solution is found and a new block is processed every 10 minutes or so on the network.
On the target,
Sure.
is that built into the protocol and it's automated, or does it manually have to be monitored and adjusted?
So it is actually built into the protocol itself. So the Bitcoin software automatically adjusts that number based on sort of the other variables on the network. So the 10-minute variable we want to keep constant, right? We always want on average our solution to be found every 10 minutes. That varies from blockchain to blockchain. For example, Ethereum is on the order of about every 15 seconds. So then the Bitcoin software running all the miners, running this peer-to-peer software, looks and sees how much computing power is on the network and will adjust that difficulty target so that the time stays constant. Does that answer your question? Yeah, theoretically it always is. It'll adjust as miners join and leave the network. They might, especially with a lot of Bitcoin forks, since there's Bitcoin Cash and some of these other ones that use the same exact mining algorithm. Sometimes, based on certain economic conditions, miners will jump back and forth for what they mine. There can be. I mean, sometimes difficulty adjustments have been known to happen that took a little bit of time because of strange conditions on the network. So our proof of work simulation using these cool little microcontrollers starts with just some essentially random data, and that's going to be our transaction block data. It doesn't really have to be Bitcoin transactions to make sense in the simulation. We then generate a random number that's our nonce and run it through a toy one-way hash function. And our result is an 8-bit block hash that we're going to be looking at to see if it meets our conditions. So now is the fun interactive part. So again, these are all over the room. I encourage you to group up together and find one of these so you can play around with this simulation. And I just have a couple notes I'm going to show you how it works, and then we can kind of go from there. So if you have one with a battery pack, just go ahead and switch the switch to on, and that'll automatically power up the device. If you have a USB cable, simply just plug it into your laptop, and there's some extra fun stuff you can do if you have your laptop on you. Okay, so once you have your device plugged in, you're going to see one red LED light up. So we are on the difficulty programming menu, and so there's a button, one of these two buttons here, labeled with a B on it. And you want to use that to set a difficulty target from 1 to 7. So let's go ahead and start with a sample run. Oh, you do have the red LED you want, though. That little green one, that's what you want. That's just for to say the board's on and running correctly, but that big red LED is... You're good. Good, excellent. So let's do a sample run at 2. So you just press the B button and you'll see this, see that increment. You'll see another LED light up. So what we're doing is we have a toy 8-bit hash. So we have numbers that are represented by 8 binary digits. And we're setting a difficulty target so that we have 2 leading zeros in that number. And we'll see a little bit more about how that works in a second. Now, I wanted this presentation to be accessible. So if you have any issues seeing red and green, or you don't see well, give the board a good shake and you'll hear it beep, and that turns on a sound mode. So you can hold the little speaker up to your ear as you program the difficulty and run the simulation, and it will actually read out to you what the numbers are. So you kind of have to give it a good jolt. It's based on the accelerometer, and it'll turn that on for you. An optional thing you can do, I believe I left them all this way, but see this little toggle switch at the top? If you make sure that is set towards the little ear icon here, V out A0, the device will log some extra information for you that you can plug into your laptop, but that's totally optional. It's going to write a log file, and when you plug in the device, you'll see a file system that you can copy and paste that off of. That's a nice thing about CircuitPython. Okay, so if everyone is there, you can actually run the simulation by pressing the A button. And what you're going to see is you're going to see a bunch of LEDs flashing on the board. And what this is this is representing the hash outputs of the proof of work algorithm and all the attempts that it's making to find a random number where the final solution you see on the board meets our difficulty requirement. Was everybody able to get a run and see some things flashing and get a final solution? You can press the A button as many times as you want to get it to run. So what you're going to see when a solution is found, the LEDs on the board are actually going to stay lit with the final block hash output. So this is our toy 8-bit hash. We're working in the 8-bit number space for this. And let's say, for example, this one that I have here on the board, we have a final hash output of 00001010. So let's break down a little bit more what this means and kind of help ourselves understand this at this smaller scale than what Bitcoin uses. So again, we're dealing with 8-bit numbers here. This is like just a toy algorithm. It would be completely insecure in the real world, but it makes this concept easier to understand. So we have a target hash with our 2 leading zeros represented in binary, and that target number is actually 32. So if you're not quite familiar with binary numbers, you have places just like you have the ones place, the tens place, the hundreds place in the normal decimal numbers that we use. You have the ones place, 2, 4, 8, 16, 32, and up from there. So you're dealing with powers of 2 instead of powers of 10. So we have a guess. Let's say this is just a hypothetical first guess. Well, we had a number that didn't start with 3 leading zeros like we're going to need to find a correct solution. This hash output with this random number is too big to meet our difficulty requirement. So we haven't done proof of work yet. We have to keep guessing. So as your board goes through many, many more guesses, we end up with a final solution where we got the required number of leading zeros. So again, this is thinking about this numerically. We have 32 as our target number. So we need to have a final hash output represented in binary that is less than 32. So this hash here is actually 10 represented in binary. 10 is less than 32. So we found a solution to our proof of work problem. Now, this might take a little bit more time, but if you're interested, here's some sort of visualization stuff that you can do with this. So I have this script here. This is a Python script that reads the log file that the device will generate if you set it up with that switch. And what we can see is over time through some sample runs, or I shouldn't say over time, as we increase the difficulty, so the difficulty target as a number gets smaller and smaller. So we go from 1 down to 7 leading zeros as our difficulty target. The likelihood that it takes a lot more attempts, a lot more guesses to find an answer to that problem increases. So for the run with a difficulty target of just 1 leading zero, on average, it took less than 20 attempts by far to actually guess and find a solution. But as we increase, we have one run where we're looking at a difficulty target with 6 leading zeros, where we went nearly up to 140 attempts, 140 guesses to find a final output that met our proof of work condition. And so you do see some outliers where in these more difficult runs, it still didn't take that long. And the reason is this is just a probability. It's not an exact condition that the more the difficulty goes up, the more guesses it's going to take. But it's about the probability of finding a solution. The more difficult proof of work is, on average, it is going to take much longer to find a solution. And this information is actually in the white paper, kind of done out mathematically, which I think is really interesting. I'm not quite that good at that level of math, but you can actually see how Satoshi proved that this proof of work method is viable for securing the network. So if you'd like to do this visualization yourself after you run your simulation a couple times, you can download this file. It's chaintuts.com/graph_pow.py. And if you plug the Circuit Playground into your laptop, you'll get a file system, and you can drag off the powlog.csv and run this Python script. So it'll actually generate a chart for you based on the unique data that you give it. So now let's kind of wrap this up by talking about this simulation versus what happens in the real Bitcoin. So this is a toy sort of algorithm. We use smaller numbers, we're using smaller computing devices to really wrap our heads around the sort of computer science concepts that go into proof of work. But there's some differences between what we did here and what actually happens on the real Bitcoin network. The first thing that's sort of a big, obvious, and important difference is the size of the numbers that we're dealing with. In our simulation, we used 8-bit hashes. The space of numbers in a single byte 8-bit number is 256 numbers total. You get 0 to 255 with an unsigned integer that is 8 bits. Bitcoin uses 256-bit numbers, and that encompasses 0 to unbelievably gigantic. So the amount of total numerals in the 256-bit number space is thought to be more than the number of atoms in the observable universe. These are unfathomably large numbers that we're dealing with. And that's really important for Bitcoin security, because if Bitcoin really used an 8-bit algorithm, it only takes 256 guesses. That's the total amount of numbers that you can run through. And so proof of work would be happening instantly everywhere, and it really wouldn't secure anything. But with numbers this big, there is no just pulling off fraud. I mean, you have to have an enormous amount of computing power. You could sit with a desktop PC or even a warehouse full of ASIC miners trying to run through the 256-bit number space, guessing, and it would take you until the heat death of the universe. It's that big that we're dealing with. So that is why Bitcoin is secure using the SHA-256 hashing algorithm. Yes? Sure.
Was it always that secure even in the beginning?
So there was less hash power on the network. So cryptographically speaking, the algorithms have been the same since the beginning. So it uses SHA-256. The process has been the same. But what has made it more secure over time is the network effect of more miners coming online and working. So as more computing power gets on the network, as miners join and leave, the more the Bitcoin software is going to adjust the difficulty and make it harder to find proof of work. And so that's by design. As mining power comes on the network, the more secure the network gets. So for example, we're talking about, you have to outcompute the rest of the network to pull off fraud if you want to try to do something malicious. In the early days of Bitcoin, when people were running on desktop PCs, and maybe you were lucky enough to have a warehouse full of servers that you could turn on, you could probably do a chain reorganization pretty easily. But that became economically unviable very quickly as more people got involved with Bitcoin because the scale got so much bigger. Does that answer your question? So some key differences between our simulation and the real Bitcoin, again, is sort of the variables that we're dealing with. So we really have 3 variables when it comes to proof of work. We have the amount of computing power, which is the amount of power that the miners are donating to the network to secure it. We have the time till we find a solution, and we have the difficulty target. So our simulation is one-dimensional. We have one single processor on one single computer, and the amount of computing power in our simulation is always constant. As we adjust the difficulty, on average, the amount of time to find a solution increases. Now, in the real Bitcoin, we have a lot of computing power running in parallel. So our computing power, our miners, is not a constant, it's a variable. It's constantly changing as miners start mining and leave mining for whatever reason. What is constant in the real Bitcoin is the 10-minute block time that we're trying to reach. So on average, we always want the block time to be as close to 10 minutes as possible. And so that's something that stays constant sort of in our equation here with these 3 variables. So what adjusts then is we have variable amount of computing power, we have 10 minutes, and so what the Bitcoin software adjusts to meet those 2 conditions that we want, which is, again, just dealing with how many miners we have online and the constant block time, the Bitcoin software adjusts the difficulty target then. So that's a bit of a difference here with what we're doing in the simulation versus what's happening for real. So again, the more power that is on the network, the harder it is to pull off fraud, the more secure the Bitcoin network gets. And that goes for any cryptocurrency that uses proof of work mining. So Bitcoin and Bitcoin Cash are definitely up there as the largest in terms of hash rate. Pulling off a reorganization on either of those would be an immensely difficult task. And even Litecoin and Ethereum, which are sort of a magnitude lower, are still just astronomically difficult to really mess with in that sense. So they all use different hashing algorithms as well. If anybody's interested in that, they all use slightly different variants. But that is how mining works. So mining is always going to occur. There will always be this proof of work process because transactions have to be processed. So what you're talking about is the block reward. So miners get two types of rewards if they solve the proof of work problem. And these rewards serve as the incentive for them to expend their real world resources, their computing power and electricity, to try and solve this problem. So the first thing that they get is the block reward, which you're talking about. This is actually the minting of new currency. So if you, and now until 2148, I think, is roughly the year when no more Bitcoins are going to be minted, every time you solve a block, you get some amount of Bitcoin reward, right? So say you get 25 Bitcoin. That was in the early days. The other reward is all of the transaction fees for every transaction included in the block. So as these transactions are grouped together, each transaction pays a miner fee as an incentive to the miners for doing this work. And so say, for example, if we're all sending each other $1 in the block, we might pay a penny fee. And the miner gets all of those fees grouped together when they solve the block as well. Does that make sense? So what the incentive will be when Bitcoin minting stops, miners will still be incentivized by transaction fees. That is definitely an open subject in sort of the debate between different chains. So Bitcoin BTC, they have, without getting too much into the weeds, Bitcoin BTC has a very limited block size. There's a limited amount of transactions that can be processed every 10 minutes. It's pretty small. And so what that does is that community wants to see a healthy fee market for doing transactions. So on Bitcoin right now, transaction fees are a lot a bit higher than they were historically in the early days. And so the idea is as things move off-chain into Lightning Network, the on-chain transactions and like channel opens and closes will still have pretty high fees that add up for the miners. The other school of thought is the sort of like the big block scaling, which is what Bitcoin Cash uses. And their idea is keep fees very low by allowing everybody to get in within 10 minutes, so you have a high block size limit. And the idea there is as you drive adoption, it's going to be by volume. So instead of having a small amount of very high fee transactions, it would be sort of the equivalent of like McDonald's making a penny on every hamburger that they sell, but they're selling billions of them. So there's two different sorts of ideas about how that fee economy is going to take place and take care of that in the future.
Do you have any plans of tackling a proof of stake simulator next?
Oh, no idea. I'm interested in learning more about proof of stake. I like to say that I'm not a Bitcoin expert, definitely. I'm here learning along the way, and I'm teaching because I love to teach and explain, and that's part of learning too. So you've given me an idea. Maybe that is a future project, or at least some tutorials on proof of stake.
Very cool. Thank you. Is the difficulty constant during a block discovery?
Yes. So everybody's working on the same difficulty, for that period. So it's always a race to find new blocks. I don't know the exact details of when difficulty adjustment occurs. But again, I would assume that everybody's working on the same target at the same time. And as the Bitcoin nodes in the network communicate and see that an adjustment is needed, I would imagine that would be sent out. And then there's, then people start working on blocks with the new difficulty. Again, I'm actually not intimately familiar with how that adjustment works.
They do a rolling average on the amount of hash power in the network. So they see that somebody has spun up a whole bunch of miners and added in X amount of hash power. They want to keep that 10-minute target with the block size. So as a result, after sampling the data for X amount of time, they'll make a difficulty adjustment to scale it up to keep that difficulty the same, so 10-minute blocks are occurring across the.
So it's every minor.
That doesn't change every block, it's like
No.
every 2 weeks worth of blocks.
No,
or
it's
something
a
like that.
rolling sampling of data, and it's continually ongoing.
Yeah, I think that was his question, is when does the difficulty, I appreciate that, Ron, thank you.
How often does it actually change?
I'm looking it up, but
now
my,
What's 2 blocks?
I think it was like 2 weeks worth of blocks,
Yeah.
something like that.
Oh, so every 2 weeks it could change to a little harder or.
It actually does. It scales up and down consistently based off the amount of hash power.
But when does it actually, when does the actual change happen?
Probably 2 weeks, like we said, 2 weeks
Yeah.
worth of blocks, so
Yeah.
whatever the sampling data is set to right now.
Every 2016 blocks.
Yeah.
So if a bunch of hash power drops off of the network, they still have to do 2016 blocks worth of work in order to get to the next adjustment, which might take more than 2 weeks.
Yeah.
If a bunch of mining power joins the network and they're mining faster, it's not going to be every 2 weeks, it's going to be much shorter.
We might be done in 10 days.
Yeah.
Yeah, again, this is a peer-to-peer protocol, and so it's all a bunch of software that's communicating with each other and making sure that everybody else is following the rules. So like the strict rules are the cryptography. You know, you have to meet certain requirements, and you know, if you're not playing by the rules, other nodes will reject the work that you're doing, and they won't propagate transactions and blocks from you. So it's really just a matter of sort of intercommunicating in this protocol. Did you have a question? So there's two sort of things that are going on. The first is there's just certain rules that transactions have to follow to be valid transactions. And so there's kind of a rule set that every transaction that's constructed is run through by all the nodes on the network. So you have mining nodes and you have full nodes, and they all verify transactions and make sure they're following the rules. So what will happen is, like, if you have a transaction that's just improperly constructed, like it doesn't have a signature or something like that, that it needs to be a valid transaction, blocks won't relay it to other nodes. So all of the nodes on the network see that it's, you know, a bunk transaction, and they're simply just not going to send it out or try to include it in a block. So you might see, it depends. Sometimes transactions, so they'll drop, they might still exist for a while, but the actual transfer is not going to occur. Yeah, it'll stay unconfirmed for a period of time until it's dropped out of the mempool. Right. I would think that if it's just completely invalid in terms of transaction construction, you know, you're just not going to see it get relayed across the network. And then the other thing that's part of this rule set is the actual cryptography that's occurring. So, you know, even if a transaction is properly constructed, for example, if it doesn't have a valid signature or something like that, you know, that's not just trusting other people on the network to sort of act together and do the right thing. Like, that's pure math, that if it's invalid, it's invalid, and nobody, again, is going to relay the transaction or include it in a block. Thank you all so much for being here.